So we should be able to do this with just a little bit of bit shifting. Well, right now our access controls go from -100 to +100. So if we add 100 and go from 0 to 200 instead, then that can easily fit in 1 byte. So we'll stick those numbers into a byte. X is going to be controller, we get X method plus 100. But then we want to take that number and cast it into a byte just to make sure it's 8 bits long. And then we can do the same thing. So shift in, select all that, copy and paste it, and change these X's to Y's. So now we have those values in 1 byte each, and the Arduino IDE stuff is based off C++, so our integers, our regular int is a 32-bit integer. So we can easily fit 2 bytes. Well, it's 4 bytes long, so even when we add in the byte for our buttons, we'll be able to fit all 3 bytes easily inside an integer, so that's our total return will still only be 1 integer long. But we're going to have to do some bit shifting to make those fit. So I'm going to start off, create a number 0. So store 32 zeros here. And then we can shift those over by 8 bits. So replace bin by whatever was in bin, shift it over by 8 bits. Not really necessary on the X one. I just wanted to go ahead and go through all the steps to make sure it's clear. Then that'll guarantee that no matter what was there, our last 8 bits are zeros. So then we can just add the X value to it. Because if those last 8 bits are zeros, and 0 plus 0 is going to stay a 0, so that's, and any ones in the binary representation of X are just going to add to 0, so those last 8 bits will now represent X. And then we can do the same thing again. So we'll take whatever was in bin, shift it over by 8 bits. Oops, looks like I missed a semicolon up here. So we'll shift it over by 8 bits, and then we'll add Y to it. And just to check and make sure all this works, let's go ahead and print out all the values so we can see what's going on. So I'll print, do a print line for the X, do a serial.println for the Y, and do a serial.println for that binary number we created. So let's save this and upload that. Hopefully it won't take too long, and we can do a quick check to make sure that is working to put those last 16 bits of the actual integer. These two are just test values. We'll delete those in a moment. Hopefully delete those in a moment. But the last 16 bits of this should be the X and Y bits put together. So let's do a quick check on that. We open the serial monitor, call for movement, and I'm going to move this over just a little. I'll move it in the negative direction, up and left. So both of them are negative, just to make sure we're getting positive numbers back. There we go, 61, 96. When we put them together, we get this number. So let's check and make sure that's the right number. I'll just do it in Notepad++ here. So I have that open. So we had a 61 and 96. 61 and a 96. So 61 as a binary number, there's 1 byte long, there's no 128s, there's no 64s, so we're going to have a 32, and a 16 would give us 48, plus 8 more would get us 56, plus 4 more to get 60, so 2 would be too many, and then 61. And for a 96, well, we don't have any 128s, a 64 will fit, and a 32 brings us up to 96. So then the rest of these are going to be zeros. And then the bin at this point is all zeros, 32 zeros. So it wasn't really necessary the first time, but we moved that over by 8 bits. So now we know bin ends with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. So then when we add 61, now bin should, well, it's going to be a bunch of zeros, but the last 8 bits should be the 61. 0, 0, 1, 2, 3, 4, 5. There we go. So that's what we should have at that point. Then we'll move that over by 8 bits again. So now then we'll have 16 zeros, then 1, 2, 3, 4, 5, 6. Then these 8 bits followed by 8 zeros. So then when we add 96, bin should now have 16 zeros followed by 0, 0, 1, 1, 1, 0, 1, followed by 0, 1, 1, 0, 0, 0, 0, 0. So let's see what value we get here. Well, we know these first 8 should get us up to 96. 1, 2, 3, 4, 5, 6, 7, 8. So that'll get us 96 plus, let's see where we at. 96, that's the 128 column. So then 256 plus 256 plus, I need to keep better track of this. So there's 256, 512, 1024. Whoops. That's not going to work to keep track of it. 1024 plus, which one was I on? Well, I got off here somehow. Let me go back a step. So we have, after we do all this, our bin should be 16 bits followed by 0, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 0, 0, 0, 0, 0. So we know these first 8 give us 96. And that's the 128 column. So then the next one would be 256. Don't have any 512s. Then we have a 1024. Then a 2048 plus, so where are we at? So there's 8 bits, 256, 512, 1024, 2048. So then we'll have a 4096 plus 4096 plus the 8,000 something, 8192. Is that right? Yeah, 8192. And then the rest of them are going to be zeros. So what will that give us? I need to grab a calculator real quick. Oh yeah, I have a calculator right here. Use this calculator. So we have a 96 plus a 256 plus 1024 plus 2048 plus 4096 plus 8192. We should have 15,712, which is what we got here. So it looks like all that logic worked out, and we'll do a similar thing for all of our controls, for our action controls, and then, well, then we do both things for the total. And this was just a check value, so we don't need that. And that'll let us know what, that way we can send all of our stuff back basically as pure binary form. and deal with those bits independently. And the return, all these returns will fit as one integer, which will make it quite easy to deal with on the script on the other side as well. And for our action controls, we only need 4 bits because the buttons are either returning a 1 or a 0. So we can do it just with 1 byte altogether, but I'll go ahead and set it so that our return type's always an integer. That'll make it easier to work with, and we'll just return an integer. So set up an integer called bin again, and well, might as well take out that redundant step because it's all zeros to begin with, so we don't have to do any shifting to make sure the last 8 are zeros. So then we'll add to that bin plus equals controller get A. We'll get the 1 or the 0 from the A. And then we'll shift those bits bin equals bin shifted 1 bit to the right. Then bin plus equals controller get B. Get the 1 or the 0 from B. Shift it 1 bit to the right. Get C. Shift it 1 spot to the right. Get D. And then we should be able to print that out. Serial.println. Print out the binary number and make sure we're getting the right thing there. And this one should be an easy one to test because, whoops, I have to upload it. So I'm going to pause while I compile it and upload it. And then it should be an easy one to test because all of our values will be a power of 2. So I'm going to pause the video while I upload this. There's no need to watch it compile. Okay, so with that uploaded, I'll hit action with no buttons being pressed and we get back to 0. Action, push button A, which should be a 16, right? No, an 8. That's right, only 4 bits. So the last one's an 8. Action, push button B, which should be a 4. Action, but C is a 2. Action, and button D should give us a 1. Yep, so it looks like all those are good, and we can easily measure the values between as well. If so, multiple combinations of buttons, we just add those together. So now we should be able to just copy and paste all this to get the last one together. So it will mostly look like this. So we'll copy the integer one, paste that in, and then after adding the y value, we'll shift the bits over by 4, then shift it by 4 bits, the 4 empty bits, since we only need 4 here, and then we can copy and paste this in. Oops. And actually, I think we should shift 5 bits over, and then this will fill in the last spot. So we shift 5 bits over, then get this and this, this. So this video, I'm going to pause and run the same test we did just a moment ago, add up the numbers, and I'll quickly show the result of that. There's no need to watch that calculation twice. But I'll run a quick test to make sure this works and try to keep this under 15 minutes here. Alright, so everything checked out. I guess the main one's this 25,344 here is the rest position. So we here in the next one we can see 25,344 plus the D button. 25,344 plus the C button. So everything checked out, and we're able to set all complete state of the controller as one integer return, which will make it quite easy to deal with on a script on the other side, whatever's receiving commands from the controller. Just wanted to include that, I guess. Well, actually, I made a silly little mistake here. I should have checked the reference material. I'm used to, or I'm not sure what I was thinking, but an integer is not a 32-bit number. Where'd that go? Checking the reference material, an int is a 16-bit, so we can only hold two. We can only store 2 bytes in an integer. We need a long to store up to 4 bytes. And yeah, I ran another test after finishing that last video, and with the joystick pressed to the up and right to the maximum value and all 4 buttons being pressed, which was a little tricky to send that command and use both hands on the controller to do that. But once I got that in there, I did get an overflow error. So those returns should be longs, not bins. So return that long. This will be a long, and I'll go ahead and make all of them longs, even here where we only need the 1 byte. And that way our return type is consistent on the other side. In our instructions, we can just say it's returning a long. Return byte. Return instead of 1 byte, a long integer for the value of each axis, and return a long integer for the value of each axis and 1 byte. And this one, to return a long integer. That way our return type is consistent if we're going to use those just straight binary. We're looking at them as numbers, but we really want to think of them as just the pure binary form. And we need a long to hold all those bits. So I think I got all those changed. So action is a long, movement is a long, and total is a long. So now our return type is consistent. So let's run a quick test on this and make sure that up and to the right with all 4 buttons being pressed does not give us an overflow. So clear this and upload this again. All right, and to try to test this, move my mouse over here right next to the controller where I can reach that with my thumb. And I'll type the word action in here. Get the mouse right above this button. There we go. So I'm pushing up and to the right on the joystick, all 4 buttons, and whoops, actually, I don't want action, I want total. Looking for total, and now pushing up and to the right on the joystick, all 4 buttons, and when I click the button, okay, we don't get an overflow error, a very large number, but really we want to think of this as the bits, not the number. So a little mistake along the way that happens, and try not to memorize we're not going to memorize everything, so remember to check the reference material when doing things like that. I should have thought of that beforehand. But now we've got that accepting the binary values, which we'll see as a number, which will also make it easy to work with in our script if we need to. So now back to finishing up the PCB videos. With just one final note before we get back to that, after filming that last scene, I did go ahead and clean up the instructions, what goes in the oxygen. So now the long integer to be interpreted as a 4-byte array, and then spelled out what's in that byte. It's like empty, 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 4 zeros, then the value of the buttons, or x-axis, y-axis, then empty x-axis, y-axis, 4 zeros, and the value of the state of the buttons. So I made that a little bit more clear, so all that's working, and that's sort of the return type we have with the normal control off-the-shelf controllers. So that's what a lot of game engines and things would be set up to work with. And again, I'm going to leave total as a specific instruction for now, but to match other game controllers, we'll probably set it so that it just always sends this back unless another instruction is passed in. But for testing, it's probably easier to do that on command. So now back to designing the PCB.